Hi, I'm Rebecca. During this lesson, we're going to look at solving triangles that are not necessarily right triangles. In particular, we're going to consider something called the law of sines. Let's look at our specific objectives now. We'll look at solving triangles and something called the ambiguous case. Now let's begin by looking at a triangle which has standard labeling. Here I've labeled vertex A and vertex B, angle alpha and angle beta, and of course the side opposite this angle alpha is labeled with an A, and the side opposite angle beta is labeled with a B. What I'm now going to do is note that we don't necessarily know that this is the right triangle right now, but I can actually drop a perpendicular, and I'm going to do that from the third vertex. So what I've formed then are two right triangles. I'm going to label this as with an H for the height of the triangle. Now what I want to do is note that if I consider just the triangle to the left, I notice that I have an angle, a side opposite the angle, and the hypotenuse of that right triangle. And therefore I can write down the following relationship. The sine of alpha is going to equal the side opposite, H, divided by the hypotenuse, B. Notice that if I do the same thing with the triangle to the right, I have an angle, the side opposite that angle, and the hypotenuse. I can write down the following relationship. The sine of beta is going to equal the side opposite, H, divided by the hypotenuse, A. Now, in both of these equations, you may note that we have the variable H. What I'll now do is solve both equations for H. In the first case, we'll multiply by B in order to come up with B times the sine of alpha equals H. In the second equation, we'll multiply through by A to give us A times the sine of beta equals H. Now, if both of these expressions are equivalent to the same thing, then we know that they're equivalent to each other. And so we can write down that B times the sine of alpha must equal A times the sine of beta. Now, in our next step, what we're going to do is just rewrite this in a slightly different version. And the idea is to come up with a nice expression that we'll end up calling the law of sines. Here, we're going to take this last step, and we're going to rewrite this equation, where what we'll do is now divide both sides of the equation by A times B. Now, what this will accomplish is to rewrite this left-hand side of the equation. The common factor of B will divide out, and we'll end up with the sine of alpha divided by A. On the right-hand side of the equation, note that the A will divide out, leaving us with the sine of beta divided by B. Now, what we're then going to notice is that these two angles were arbitrarily chosen as alpha and beta. And so, in a similar manner, what we could show is that you could rewrite that the sine of alpha over A would be equivalent to the sine of the third angle, which we could call gamma, over C. And this leads us to something called the law of sines. And now, let's formally define that law of sines. Any triangle with standard labeling satisfies the following equation. The sine of alpha over A equals the sine of beta over B equals the sine of gamma over C. Equivalently, we could write the law of sines as A divided by the sine of alpha equals B divided by the sine of beta equals C divided by the sine of gamma. Now, we're going to use the law of sines in our next example. If we're given that beta is equal to 85 degrees, gamma is equal to 40 degrees, and B is equal to 26, we want to solve the triangle with vertices A, B, and C. So solve triangle ABC. We're going to begin by doing a quick sketch of this triangle. What we can now do is notice that if you start off by labeling beta with 85 degrees, I'm going to draw an angle here which is slightly less than a right angle. And I'm going to label this with the 85 degrees. And that's going to be our beta, recall. Notice right now that I'm given that this length opposite beta is 26, because that's my value of B. So I'm going to go ahead and put in another 40-degree angle into this triangle, and I'm going to go ahead and connect these dots and put that 40 degrees at this vertex. And then I have that B, opposite beta, is going to be 26. Now, using the standard labeling, what we're going to have then is, if this is gamma, then we're going to have opposite gamma, we're going to have our value C, and we're going to have an angle alpha, and we're going to have opposite alpha, the length A. What we want to do to solve the triangle is to find the values for alpha, A, and C. Now, the first thing we can do is to find alpha. And of course, we're going to use the fact that 3 angles in a triangle need to add together to give us 180. So to find alpha, we're going to take 180 degrees, and we're going to subtract from that the sum of the other 2 angles. So we're going to have the 40 degrees plus the 85 degrees subtracted from the 180. That gives us alpha equals 180 degrees minus 125 degrees, which leaves us with 55 degrees. Now what we're going to do is to find side A, and we can do that using the law of sines. In order to use the law of sines, what we note is that we're going to need to have an angle and a side opposite that angle given to us. And of course we are in this particular case, given that information. Let's start off by writing down A over the sine of alpha equals B divided by the sine of beta. Now I've chosen to write the law of sines in this format because what we're looking for is going to be a length of a side. So I'm choosing to write the lengths of the sides in the numerators. I can substitute in known values now. We'll have A divided by the sine of 55 degrees equals the length of side B, which we're given 26, and the measure of angle beta, which was 85 degrees. Now to solve for A, what you can note is if we multiply both sides of this equation by the sine of 55 degrees, we'll end up having A isolated. Let's do that now. We'll have A is equal to, and we're going to go ahead and put that multiplication by the sine of 55 degrees as part of the numerator. And now what I'm going to do is use a calculator in order to get an approximate value for A. Here, we want to go to the calculator and make sure that we're in degree mode. Noting that, we're now going to substitute in the values that are given. We're going to have 26 multiplied times the sine of 55, and then we're going to divide that by the sine of 85. And we come up with a value which is approximately 21 4/10. Let's write that down. A then is approximately 21.4. Now in this particular problem we weren't given any units, so therefore we're just going to leave it at that and say it would be 21.4 units, whatever those units may be. We're now going to continue on with this problem because we found alpha and we found A, but recall that we were asked to solve the triangle in total, which means that we now actually need to go back and note that we still don't know the value for C. Again, what we can do is use the law of sines. And this time, what we're going to do is write down the equation in this format. We're going to have C divided by the sine of gamma is equal to B divided by the sine of beta. We want to use the value of B here instead of the value of A, since A was an approximation that we came up with. Let's substitute in our known values. C is what we're going to be looking for. We're given that the angle opposite C is 40 degrees. Our B value is 26, and our beta value is 85. Again, following similar steps, we're going to solve for C by multiplying both sides of the equation by the sine of 40 degrees. And once again, let's use the calculator in order to come up with an approximate value. Here, what we're going to note is we can take 26 multiplied times the sine of 40 degrees and divide that by the sine of 85 degrees in order to come up with an approximate value of 16 8/10. And writing that down, we have C is approximately 16.8, and that then completes the problem. Now it's your turn to try a problem where you're going to be using the law of sines. Here's the one we'd like you to attempt. If beta is equal to 36 degrees, alpha is equal to 72 degrees, and A equals 15, solve triangle ABC. Let's see how you performed on this problem. We're going to, again, start off by noting that we're given two angles in the triangle. Now, in my first example, I went ahead and graphed the triangle. That's not really necessary in order to be able to complete the problem, though. We can just use the given information and work from there. Since we have two of the angles given to us, we know we can find the third angle, which in this case is gamma, by taking 180 degrees and subtracting from that the sum of the other two angles. And evaluating this, what we note is that we'll end up with 180 degrees minus 108 degrees. And so we come up with gamma equal to a length of, an angle measure, that is, of 72 degrees. Now, one thing to note here is that we end up having an angle which is equivalent to one that was already given, which means we're working with an isosceles triangle. That's going to be important to us and actually make our work a little bit easier. Now, if I do a quick sketch at this point, what I could note is that quickly sketching out an isosceles triangle, I have a 72-degree angle, which we could call, that's angle alpha. We have another 72-degree angle, which is going to be our gamma. We know the side opposite alpha is 15, and so now let's just note that because we know some information about isosceles triangles, that the side opposite these equal angles will be the same on both cases. We can actually say now that this other side must be 15 also. So what we note then is that C has to equal 15. Now let's think about what we haven't found yet. We were given the value of beta, we were given alpha, we found gamma, so we have all three angles. We have our value for A, we have our value for C, and what that means is what we're having to do next is to find the value of B. Let's write down an equation that's going to help us. That equation is going to be the law of sines. We're going to write down B divided by the sine of beta is going to equal A divided by the sine of alpha. Here, let's go ahead and substitute in known values. B is what we're trying to find. We can write down the measure, that is, of the angle opposite B, that's 36 degrees. That has to be equivalent to A, which was 15, divided by the sine of 72 degrees. Again, let's go ahead and multiply through by this denominator in order to solve for B. B will then equal 15 times the sine of 36 degrees divided by the sine of 72 degrees. And again, let's use the calculator in order to help us. We're going to evaluate this by substituting in 15 sine 36 degrees divided by sine of 72 degrees. And we come up with a value for B, which is approximately equal to 9 3/10. And writing that down, we come up with then the solution to this equation. Now, the next thing that we'd like to consider will be an application problem. And so we're going to look now at a problem having to deal with bearing. An ore ship is traveling west toward Duluth on Lake Superior at 18 miles per hour. The bearing of Split Rock Lighthouse is 285 degrees. After 1 hour, the bearing of the lighthouse is 340 degrees. Find the distance between the ship and the lighthouse when the second bearing was determined. Now, key to being able to look at this problem correctly will be to get a good sketch. So let's review how we're going to do that. We're going to start off by saying that we have a ship at a particular location. I'm just going to use a dot here in order to indicate that. And we have a lighthouse, and we're told at this point in time that the lighthouse is at a bearing of 285 degrees. So what we're going to do is actually draw in a north-south pole. Notice that then we would have east and west in this manner. And I'm going to use the bearing of 285 degrees, recalling that we always measure bearing clockwise from due north. So that means we're going to start here and we're going to think about a movement around clockwise 285 degrees. Now that goes just a little bit past 270 degrees to approximately here. And now what I'm going to do is draw in that angle. We have a lighthouse somewhere in the distance, and the lighthouse I'm going to indicate with this mark. What I'm going to now note is that the ship travels due west, and that means I can sketch in a horizontal line extending toward the west. And in fact, what we're told is that the ship is moving at 18 miles per hour, and we're only interested in what happens after 1 hour. And what that means is we can actually substitute in then the length of 18 here. Now recall the 285 degrees. We end up going 3/4 of a full revolution, which would be 270 degrees, and therefore the excess that we've ended up moving would be another 15 degrees. So I can label this angle as 15 degrees. At that point in time, after the ship has traveled 18 miles, what we note is that we have a new bearing, and that bearing is 340 degrees. Let's again quickly sketch in a north-south pole here. 340 degrees, again, moving from clockwise from north would be almost a full revolution. And I'm going to go ahead and now put in a length which corresponds to that information. In this problem, if we had gone a full revolution around, we would be at 360, which means that this small angle here must be 20 degrees. 340, the difference between 340, that is, and 360. Now, the way we're going to use that is the fact that we could either say, well, if that's 20, then this is 70. Or notice what's really important is we'd like to get this angle here. If that's 20 degrees, then we have another 90 degrees, giving us then for this angle in total 110 degrees. Now, the problem asks us to figure out what the distance is between the ship at this point in time after it's moved the 18 miles and the lighthouse that was given. So let's look back and identify which length we're concerned with on this triangle. Here, the length that we'd have would be the ship's present location and the distance between that location, that is, and the lighthouse. So we're going to label this with our unknown value, and we can use any variable we'd like. In this case, I'm going to use the value of x. Now notice that we do not have a right triangle in this picture. In fact, what we notice is we have a 15-degree angle, a 110-degree angle, and of course we can find the value of the third angle also. Let's go ahead and do that. And the way to accomplish that is to take the 180 degrees and subtract from it the sum of these two angles, which would be a 125-degree angle, 125-degree sum, which is going to then give us a difference of 55 degrees. So the angle that we have up here on the top of our drawing then is going to end up being 55 degrees. The reason this angle is so important to us has to do with the fact that notice that the only length that we're given in the problem is the length of the side opposite this angle. And because we're given that length, we note that we can use the law of sines. We're going to have an angle and a side opposite given, and we have this angle and the side opposite that we're trying to find. Let's go ahead now and write down the appropriate relationship that we're going to come up with law of sines. We can write down that this is, since this is what we're looking for, we'll have x divided by the sine of the angle opposite x, which is 15 degrees, is going to equal 18, the given length, divided by the sine of the angle opposite that length, which is the 55 degrees. We can solve for x in the manner similar to the ones that we used earlier. And now again, let's use our calculator in order to come up with an approximate value here. Substituting into the calculator, we'll have 18 multiplied times the sine of 15 degrees, and we'll divide that by the sine of 55 degrees. That gives us an approximate value of 5 and 69/100 miles. And we know that we're dealing with miles because of the fact that the other value, the other length that was given in the problem, was in miles. So writing down our solution, we come up with x approximately equal to 5.69 miles. And what we can then interpret is that the distance between the ship in this present location and the lighthouse would be this measure. Now let's consider problems where we're only going to be given one angle. Here's our first example. Let's let alpha equal 65 degrees, A equal 4, and B equal 12. If possible, solve the triangle. Now notice again, we don't know that this is a right triangle, and so therefore we're going to note that we have an angle and a side opposite that angle given to us, and that leads us then to the law of sines. In this case, notice that what we're going to be looking for to begin with will be an angle beta. And so for that reason, I'm going to set up the law of sines as follows. I'm going to write the sine of beta divided by B equals the sine of alpha divided by A. And now let's substitute in our known values. Beta ends up being our unknown. So we'll have the sine of beta divided by the length 12 equals the sine of 65 degrees divided by the length 4. Now we're going to solve for beta by multiplying both sides of the equation by 12. That will give us that the sine of beta is going to equal 12 times the sine of 65 degrees divided by 4. Let's now use the calculator in order to come up with an approximate value for this expression on the right. We're going to have then that 12 times the sine of 65 degrees divided by 4 gives us a value of 2.7 approximately. Now let's go back to the problem and think about what that's really saying to us. We now are saying that the sine of beta is approximately equal to 2.7. Do you notice a problem with that? Well, you might recall that the value of sine at its maximum is equal to 1. And therefore, there is not going to be a triangle that's going to fit this description. And so what we're going to have to say in this particular case is there is no such triangle. Or you could say in the problem that there's no solution. Let's now look at a second example. In this problem, we're going to have beta given to us as 54 degrees, A is equal to 24, and B is equal to 22. And we're asked to solve the triangle. This time, notice that the angle that we're given is beta, and the side opposite it is 22. Setting up an equation in a similar manner, we're going to have sine of alpha over the value A, which is 24, is equal to the sine of beta, which is 54 degrees, divided by 22. Again, multiplying through by the denominator, in this case, is going to give us 24 times the sine of 54 degrees divided by 22. Again, let's rely on our calculator to give us an approximate value here. We're going to substitute in 24 times the sine of 54 degrees divided by 22. We come up with a value which is approximately 88/100. Let's write that down. We'll have the sine of alpha is approximately 88/100. Now, again, let's think about what this is actually telling us. We can actually find alpha in this particular case by taking inverse sine, and we'll do that in a moment. But the other thing to note is that this value is actually less than 1. If we just do a quick sketch of that sine graph, you'll note that if we think of the value 1 as being our maximum, then the value, which is approximately 0.88, is just below that. And actually, extending this line across, you'll notice that there are 2 times that this value actually appears on our original graph. What that leads to is something called the ambiguous case. Let's show you how to proceed with this problem in that manner. To begin with, we're going to solve for alpha by doing inverse sine. Now, I wrote down the approximate value here, but actually, what I would use on my paper would be to write down that this alpha is equal to the inverse sine of the expression in its exact form. And in fact, on my calculator, this is how I would want to insert that. So we're going to, again, go back to the calculator. And one thing that we can do on the calculator is say that we're going to do inverse sine of the answer that we came up with previously. That's as opposed to having to rewrite all of those terms. When we press enter here, we come up with a value for alpha, which is approximately equal to 61 point, well, actually, we need to round that off to 62 degrees, don't we? And so we're going to end up writing down then that alpha is approximately equal to 62 degrees. Now, because we note that we have actually that 62 degrees in what we could think of as, cutting this right down the middle, like quadrant 1, and we also have a quadrant 2 angle that would fit that description, we can find that second value for alpha by thinking about this as the reference angle. We'll label this alpha sub 1 equal to 62 degrees, and we'll find our other possible angle by subtracting 62 degrees from 180 degrees. That's going to give us then a value for alpha sub 2 of 118 degrees. Now we need to make sure that this is actually going to give us a second triangle. And the way to do that is to note that if we take 118 degrees and add to it the given value of 54 degrees, we do not end up exceeding 180 degrees, which means there's actually a second triangle that's possible from this given information. Now what we're going to do is leave it to you to solve this last example completely. That is, you're actually going to take both values for alpha and independently find the other values that are unknown at that point. That is, you're going to find the third angle in each case and also find the third side. So we'll leave that for you to do on your own, as well as for you to try problems from your textbook that complement this lesson.